Do we have the heat capacities for A and B? Yeah. Do we have the initial temperature?
Yes.
Yeah. Do we have this delta Cp? Is that given? Okay, so how do I get that? Like you want more than just the person in front of you to hear.
Sum of the stoichiometric coefficients times each individual.
Yeah, it's the same thing, right, as what we did for the delta H. The stoichiometric coefficients are there. In this case, they're all 1 or -1. So now it's the heat capacity of C minus the heat capacity of A minus, sorry, B minus A. Doesn't matter, because in this case, they're actually the same. So that's what you get. And if we look at our numbers, you get 30 minus 15 minus 15. 0 in any units. That's convenient. A lot of times, the problems will be rigged so that the delta Cp is 0. Not all the time, but you do see that a lot in these problems, that they're set up for that to happen. All right, so do we have everything we need? Yeah, right? All right, so we plug it all in, you get 0.85 times 6,000 now to go into calories. Right now it's in kilocalories. I'm being lazy with units. I would never recommend that you guys do the same. 30 times the initial temperature. Third term goes away, right? Because delta Cp is equal to 0. And then the numerator is just, the denominator is just 30. The sum of those two, again, that third term goes away.
Why isn't the 6,000 negative?
Why? Because that's negative there.
Oh.
All right. That's what you get, 470 Kelvin. Why did we need to know the temperature?
So you can go back and temperature.
So that we could get the rate constant.
Where'd you get that 30 from?
Where did I get the 30 from?
I know.
15 plus 15. Any other questions? Okay. So we'll leave some of this up there. Get rid of this stuff. Okay, so we were given that K at 300 Kelvin is equal to 10 to the minus 2 liters per mole seconds. So what do we need in order to get K at the temperature we care about?
Divide them?
Yeah, this is where there's multiple approaches that you can take. So the approach I'm going to do on the board isn't the one you have to use. And I think in the book, there's literally just a formula that you'll jump straight to that formula. The reason why I don't like it, and I think I'll put it on the board here in a second. Thought I had it. I don't, sorry. I don't like it because he puts in like T2 and T1 and like he introduces some more temperatures. And what he's talking about there is like this is maybe T1 and then T is the reactor temperature. But it's confusing if you have multiple streams, so anyway. Let's just do it a simpler way. This is equal to, it's not the most time efficient method, but it's obvious and not confusing. What do I know on the right hand side? R and T. I'm only missing A. So let's solve for A. It's going to be and what was the activation energy? I can't read this. Can somebody? 10 kcal. Right. So I'm going to put 10,000. And then you divide it by 300, which is the temperature, times R in units of calories, which is that. 1.93 times 10 to the 5th. All right, and what do I need? At what temperature? All right, so K at 470 Kelvin. A is now the same. Activation energy is the same because we assume that it's constant with respect to temperature. Temperature is the only thing that changes. So we get 4.32 liters per mole second. Yeah?
How big of a change does it have to be to take into account? Because 170 is kind of big.
The activation energy?
Yeah.
That big, big, big.
Mhm.
That's a good question, though. I'll run some actual numbers because I calculate these things all the time, but I can't remember an example off the top of my head. But I'll run some numbers. All right, now I've got a rate constant. Come back to this formula. At this point, we've gotten all the use that we're going to get out of this energy balance. For a CSTR, it's pretty simple. All right, so the volume is flow times conversion divided by rate constant, concentration squared, 1 minus conversion. Is there anything up here we don't know?
Molar flow rate.
Yeah, we don't have FA naught, right? So how do we get it? CA naught times what? The volumetric flow rate. .2 moles per second. So the volume of a CSTR is going to be 0.2 times 0.85 divided by Any questions? Again, I'm being very reckless with units. Don't do that. Yeah.
I think the units are wrong for flow, because you give us flow rate in liters per second and concentration in moles per
Kilomoles per meter cubed is the concentration. And then you get 2 liters per second, which is 2 times 10 to the negative 3 meters cubed per second. That's where your unit conversion comes from. I'm not saying they're correct, but usually they are. These notes are old, so I hope most of the issues have been solved by now. So, 175 liters. Any questions? So this is fairly straightforward, right? When it's an adiabatic reactor and a CSTR and you're given conversion. So there's lots of reasons why this has become a straightforward problem. But let's not mess up the straightforward one. Yes?
So if we're trying to check this for reasonableness, what would be like a good ballpark for these volumes or other things?
Reactor volumes can vary by huge, huge amounts. I don't think any of the problems that you're assigned were given scrutiny to sort of assess whether or not you end up with sort of a physically reasonable number. But I mean, you can have reactors that are hundreds of gallons without any issue. And you could have a 1 gallon reactor too. Of course, what matters more is, right, I mean, it's always going to be the volume over the flow, right? If I go to a higher flow rate, I need more volume.
In homework 2, there was a problem. They gave a graph where the axis was like 100,000 meters cubed, and that was around the range of the reactor volume.
Right. So, yeah, like I said, I don't think that the problems have been checked for their reasonableness in terms of the scale of the reactors that'll come out. Something for you to worry about in your design class, I guess. All right, so part B. We're going to change things a little bit. We're going to find x for okay, so we just did, you're given a conversion, you're asked to find a volume. This one's a little bit different. I'm giving you a volume, you've got to tell me the conversion.
Do we know the temperature?
Nope. You do not know the temperature. Otherwise, this would be no different from a CSTR problem that you got in the first half of the class. Right? You would just calculate the rate constant at that temperature and solve the design equation. So what do we do if we're not given the temperature?
Solve for temperature and the energy balance and look at that
Same equation,
Or
we just have the energy
backwards.
balance of X in terms of.
Well, let's start with the material balance instead of the energy